very much for the very kind introduction. Thank you very much for being here. Thank you very much for giving me the chance to be here. I'm very grateful for that. What I was try to be, was saying thank you. Thank you to be here. I really, really appreciate it. I love it being back in India, being back in Delhi. I was so grateful to be here at the first Indian Geophysics conference as well. So it's really fantastic to be back and to actually continue the story. I had a presentation about airborne geoscanning 4 years ago, and there was the question in the room, have you done this in India? And I said, yeah, we're just about to start. And now I can actually show you what we did years and years and years ago actually in India. So that's even more exciting. I'm very happy to have the chance to do that. But I will not only talk about that, about the Himalayan tunnel projects. I will try to really highlight these important factors that have been also so beautifully already described in the inaugural session, that we can hide, not that we can hide, that we can unlock so much hidden value via the use of geophysics and by really translating geophysics to actual engineering parameters. So really making that leap forward, not only talking about our beautiful science of geophysics, but really making it relevant. So I'll start with the tunnel project from India, and then I'll take it a little bit further. As I'm the first talk that talks about airborne EM or helicopter tunneling EM, I'll just stop a moment to remind us what this method is. It is an induction method, usually carried out from a helicopter, sometimes from an aeroplane, but in the geotechnical world, usually from a helicopter. You induce a quite strong current in a transmitter coil that hangs under a helicopter, and then you switch off that current as fast as technically possible and induce an electromagnetic pulse into the ground by doing that. And that pulse will slowly, quite fastly, disappear in the ground. And by inversion, we can get a signature model that explains that deeply. That's basically what airborne electromagnetics is. That is the key method that I'm talking about. And as the title suggests, I'm talking about using that in probably one of the most extreme environments you can think on this lovely planet, and that is the Indian Himalayas. So this was really an absolute adventure to carry out these measurements in such a harsh environment. We were collaborating with the Indian Air Force that supplied really heavy-duty gear to lift these instruments in these extreme high altitudes and to carry out these measurements. It was almost deemed impossible to do this in these high altitudes. A normal helicopter can't fly, can't start with 500 kilos hanging under it. But we made this happen, as I said, in an enormous collaboration with the Air Force, which was an amazing experience. And we definitely set some world records here, flying these sort of things at 5,500 meters above sea level. This was made possible, and we managed with that to look into the ground in a completely inaccessible area. Right? That's really what the story is. It's about pre-investigations in an almost inaccessible area. So just two highlights from those results some years ago. We did some work on one tunnel that actually was already under excavation. This was kind of our calibration spot or validation spot. And if you zoom a little bit in, or if I zoom a little bit in, into one particular area of that model, what I'm showing here is just a long section through the geophysical models. So these are just the resistivities we're looking at on the bottom. And on the top is the conceptual geological model pre-construction of the tunnel. And you see some different colors there, some bluish colors which are more weaker rock types in that particular setting, and the greenish colors are the more competent rock types. Now, when we did this, when we showed the preliminary results actually to the engineers at the field that were building that tunnel, they were really excited to see that, because they could confirm that somewhere down here, they could confirm that after the portals they had really challenging rock conditions, really weak rock, and then at some point after the portal they got into the better rock. And then you kind of see that same signature here in the resistivity models. Not a big surprise for us geophysicists, but a very nice validation to see that this is actually the truth, right? Even though, of course, it has its limitations in resolution. This is not a microscopic image of the geology, it's a fuzzy image of the geology. So moving on from that kind of validation setting, we look at the models that we derived from one of the tunnels that was actually investigated. And here, we're already looking at a 3D model that really just illustrates, it takes out two particular units, two particular types of rock. This is validated, correlated to that other setting. So we're looking at the weaker rock types in, now let me get the colors right, blue, and the stronger rock types in yellow-ish. And what you really can't see from the distance in the 3D model is that the core drillings that were available along that route, almost all of them really only shows the weaker rock type. Hardly any of them hit the stronger rock type. But the actual 3D model that looks, over the whole area of the project could reveal that there were definitely pockets, not just pockets, but segments where the tunnel was going to go through the nicer rock types that would be not so expensive to build in. And if you, is that thing turning now? I hope I didn't break it again. It doesn't want to turn. Well, imagine there's a 3D model that is now spinning around and you can really see all the details, which you could if it would work. And that would tell you, right, where is the planned alignment, in which rock unit, where is it transitioning, at which angle, and that gives you arguably a really good basis of information to do your follow-up work.
This is the result of airborne?
This is result of the airborne,
which
absolutely.
technique?
With a SkyChem 306 system. Yes. No problem. But these have been the old results from the Indian Himalayas. But now I really want to take it one step further and talk about, unlocking the hidden value. And that's where we really see an enormous value of applying various machine learning techniques to take these fantastic 3D models from the geophysics, but they are still only geophysical models, right? But take them as a basis and apply various types of AI on those with the help of a few boreholes, and then extract models that actually tell you the geology. So models that still are fancy and colorful and 3D, but they are not showing the resistivities any longer. They're actually showing the geological conditions. And I'm just going to highlight two use cases how that can have an enormous impact on your engineering project. The models that you see here now, that is a bedrock topography. Right? So this is what we see here. We've revealed the sediments. We're looking down somewhere between 20 and 150 meters under the ground, and we are really just imaging the top of rock. And we do that by, again, flying an airborne EM survey over that whole area, taking a handful of boreholes that are available in that area, throwing them into an artificial neural network, and extracting the visual topography. And doing that actually before the detailed ground investigations for that particular project have even started. And having that information at that time revealed at this project that this here, which was a planned tunnel, which was planned to be in hard rock, it wasn't in hard rock, it was actually in really soft sediments. And before even the first drilling was taken, the alignment of the tunnel was just pushed a little bit further to the west, and then the tunnel could be constructed there as planned. If that information would have been available, if the normal drilling program would have commenced a year later, it would have been too late to change the alignment, and we would have had to build it in that kind of condition and would have lost about $25 million in this example of just a 3-kilometer tunnel. Avoiding expensive mistakes by revealing the ground conditions very early. And then, of course, when I show things like this, the question always pops up, how accurate is this, right? What's the resolution? What's the accuracy of that? And of course, it's not in a centimeter scale. Of course, it's not in the fantastic resolution that you get from your one SPT or from your one core drilling. But you only have 1 or 10 or 50 of them. You never have thousands of them to really understand what's going on. And to illustrate what is the resolution that we can get from that, I brought these two examples where you see a similar, bedrock topography model, images here, And this guy here is produced by the helicopter EM, and only 3 boreholes, whereas the one on the bottom contains almost 1,000 boreholes. So you see there are some tiny differences, of course, but the major features, the major structures, they are there with only a handful of boreholes. And if you want to do this very mathematically, then you can do all sorts of back validations, and you can actually calculate how many meters accuracy do you get, depending on how many boreholes that you throw into your workflow that you have with work. So that's just a word about resolution, and then almost closing towards the closing. That didn't make any sense, but I think you know what I'm saying. I want to just talk about the other taste of machine learning, not looking just at geometries, but actually already looking at the geology itself, looking at the type of material that you will encounter when you start to do your excavation work. So, showing the resistivity model, this is just a starting point, that's not the result. But having a number of samples from the area that actually identify what kind of soil type you're talking about, and throwing that into another branch of machine learning workflows, you can actually get a model like this. And this model here is actually showing the mechanical properties of the sediments that will be encountered when this railway is being built. So the different colors actually mean the different classes of SPT counts. Again, extracted from the resistivity model with a few target samples through the machine learning. And of course, also in that setting, you have the bedrock model in addition. I'm just not discussing it right here. So that's really 2 examples about how we really can unlock stuff in the framework of what we've done in the Himalayas. I'm going to jump over this one and just come to my conclusion so that we have some time also to discuss and answer questions, which there surely are. But I do hope that I managed 80% in the room, that we can certainly unlock hidden value by translating geophysics to engineering relevant properties. And if we think back about what was the original title of the talk, it was about tunneling. Yeah, what's the main focus areas of airborne EM for tunneling? Of course, yeah, it's overburden mapping or overburden justification, and it's weakness zones or weak rock types, as illustrated in the very beginning. Thank you very much.
Good morning, everyone. I am Akhil Mishra from CSIR National Geophysical Research Institute, Hyderabad. It's honored to be here and present on joint interpretation of electromagnetic and magnetic data. How magnetic data can help in AM resistivity interpretation. And I will be showing a case study from Konkan Railway Tunnel project, and the title of my talk is Role of Airborne Magnetic in Delineating Weak Zones Vulnerable for Tunneling in Hilly Region, and Joint Interpretation of Airborne Magnetic and EM Data. Tunneling is required for any infrastructure development. It is very important for rail, for road, for headrest tunnel, any type of, in particular in hilly region. And for tunneling, this subsurface geology, overburden information is required. And in this regard, geophysics plays a major role for giving insights about the subsurface condition and geology, geotechnical investigation, hydrogeological settings. But like here you can see like this hilly terrain taken from Konkan Railway Tunnel project. The ground-based geophysics cannot be implemented, and it is very difficult to acquire data. So generally, airborne geophysical survey is carried out, and in airborne geophysical survey, mostly airborne time domain electromagnetic and magnetic survey are carried out. AM resistivity, AM data provide resistivity sections which give resistivity in the subsurface, which can give weak zones and other based on resistivity. We can delineate weak zones or some contact faults. but it has some limitation, like at certain areas, AM data need to be deleted because of power lines or other installation as it is active source. So it is more affected by this ground-based installations. And also it has depth limitation because it is very hard to see beyond 500 meter. Even in hilly region, if rock is resistive, we cannot see up to 300 meter to beyond 3 to 400 meter. So in such cases, airborne magnetic data, which is generally acquired with the EM, can help. And now in this presentation, I carried out exercise how jointly magnetic and airborne electromagnetic can help in delineating weak zones. So the challenge, like for this area, the challenge is like complex geology and geophysical settings. It is part of Western Dhaba Craton, and it has many lineaments, many weak zones, many streams, and its subsurface extent is not known, and which can be vulnerable while tunneling. So we went for airborne electromagnetic and magnetic data acquisition. This is a data is required using SkyTem 312 system. It has for electromagnetic, it has dual moment system, high and low moment, giving information from very shallow to deeper region. As well as aerometric data is required using CDMR micrometer from hilly bone as well as from base stations. Like routine processing has been done for AM, like filtering, averaging, and deleting the noisy data. And following the inversion of AM data, we get resistivity depth sections. Similarly, aerometric data is processed like protein processing, correcting for diagonal correction as well as IGRF corrections. Now we have magnetic data and resistivity depth sections. So now we applied a very popular method actually, that is extended Euler deconvolution. So Euler deconvolution technique is, I think, well known, but Musendu et al. In 2001 developed this technique, which is just constraining the solution from Euler homogeneous equations. So this right in red box I have shown the simple Euler equation and its extended Euler equations. So for the methodology, the process is first we solve the Euler equations for structural index, which is dependent upon the source geometry, like it is fault or it is contact or it is dike model. So first we solve the simple Euler equation, like equation 1 for structural index 0 and 1 using least square method for a particular window which has sufficient data points like 15 to 20 data points, and we find one location x1 and z1.
Mr. Akhil, you please leave the theoretical part, you come to the main part, because otherwise you will lose time.
Okay. So generally we calculated solutions and we rejected those solutions which has relative difference less than 10%. Then we find some z value. Now we implemented along tunnel lines, and you can see first time this magnetic anomaly data which has some gap, which data is deleted because of the noise, as well as in resistivity there sections at here, and it has also gap. It has, because of some installations, this data is also deleted. And this second pan showing extended Euler solutions for type and as contact model, and we delineated based on joint interpretation, like where resistivity, low resistivity as well as Euler solutions, though they marked as fault or contact zones, and they are correlating with the subsurface geology, like here some streams or some faults or some contact is there, they are correlating well. So in this way, like this portion, we don't have electromagnetic data, but we have Euler solutions from NGRI data. So they are representative of some weak zones or contact zones. So and this exercise has been done along several profile lines along the tunnel as well as parallel lines. So if these solutions are continuing all three parallel lines, we have taken lenses for one other representative profile, and here also we mark several faults and geological contact zone and matching with the geology and known lineaments as well as faults. In this way, like for any tunnel constructions, we can give what are the probable vulnerable or weak zones that may pose problem while tunneling, and we can give results in tabular format at what distance and at what depth is there any fault zone or contact is there or not. So major conclusions is the combination of airborne electromagnetic and magnetic survey aids in obtaining a comprehensive understanding of the subsurface condition in hilly areas, thereby facilitating better decision making during tunnel construction. And this results from this tunnel projects have inferred several weak zones which may be vulnerable while tunneling. I sincerely acknowledge Dr. CSIR-NGRI Hyderabad for giving permission to present this paper here, and also acknowledge Konkan Railway Corporation Limited for sponsoring and approaching NGRI to conduct a survey. Thank you very much for your kind attention. Airborne data is collected using Skyton 312 system.
Who has selected it?
NGRI.
Okay.
And we all might see in the schedule, the next up is Dr. Arindam, but due to some health emergency, he cannot join us today. And so we move on to our next author. This is Mrs. Khadija Achouri. She's a geophysical engineer from Sonatrach, Algeria. Please welcome her with a round of applause.
I'm Achouri Khadija, and my colleague Akhil Mishra, a geophysicist at National Geophysics company in Algeria, on Algeria division Sonatrach. Today I have the honor to present our case study, titled Enhancing Deep Information in Algerian Seismic Data using Tomography Refraction Statistics. Our case study delves into the inversion method to unravel the complexities of Algerian geological structures. Offer a case study to showcase the effectiveness of tomographic refraction statistics in seismic data analysis. So, have you ever thought about the challenges scientists face in extracting accurate geological information from seismic data? What specific near-surface factors will raise the static challenges in seismic data interpretations? How can we unlock deeper insights from Algerian seismic data to better understand the Earth's subsurface using tomography refraction statistics? What limitations have been encountered in traditional seismic methods when it comes to visualizing and interpreting near-surface structures? In our case study of southeastern part of Algeria, the focus lies on understanding geological aspects, particularly the variation within the weather zone, elevation, and the refractive elevation, which have a direct impact in the statics and quality of our seismic data. By employing static methods, especially tomography methods, aiding to enhance the quality of our subsurface images. Let's briefly introduce the region. Our case study is located on the southeastern part of Algeria, between the basins of Wad Mia in the west and Berkine in the east. This study consists of reprocessing with mesh of several phases carried out between 1998 and 2017. It means a total of 15,000 square kilometers. The southern part of the study area presents a more complete Paleozoic and the thickening of the evaporitic deposits. Here we have the main effects of near surface. One of the most relevant data processing problems for land static seismic data involves the travel time calculation of the weathering layer often exhibits a high degree of variability in propagation velocity. elevation differences across the survey area, impacting the travel path of seismic waves and introducing static shifts. The refractor delimits the interface between the weathered layer and the consolidated layer below. And the refractor morphology, it is influenced by geological phenomena such as stratigraphy, faulting, and folding, and leading to uneven energy distribution in seismic data. By comprehending these intricate relationships and using the methods of static corrections, we can explore the complexities of near-surface effects. The static methods address the elevation and the refractor elevation differently. First is GLI, generalized linear inversion, employs linear inversion to estimate the layered velocity model. DLM is differential refraction move-out, focuses on differential refraction move-out corrections. The last one is interpolated upholes, use upholes data to interpolate refractor properties. Tomographies offer several advantages over these static methods. Why tomography can be more effective? Firstly, tomography using gridded model for the inversion addresses the morphology of both elevation and refractor by constructing velocity models that capture variation in subsurface properties. Secondly, tomography utilizes the principle of ray tracing, taking into account the intricate pathways seismic waves follow through the subsurface. Lastly, tomography has a sensibility toward the quality, also the high density of shots and receivers. The essence of travel time tomography is that the level is the travel time associated with a given ray is integrated slowness along the ray, as mentioned in this equation, is the integral of slowness, which is the reciprocal velocity. It means 1 divided by the velocity at the spatial and vertical coordinates, XZ, and yes, a differential distance along the ray. The approach traditionally used in tomography is to linearize this equation about some initial or reference slowness model. When this is done, the discrete form of linearized integral equation for a collection of rays is delta t equal d delta s. In the inversion, the velocities are assumed to be constant in cells, as mentioned in the figure here. By employing tomographic techniques and considering turning rays from various source received configurations, it is possible to iteratively estimate the velocity distribution within the weathered zone, compare observed and predicted arrival times to refine the model until errors are minimized. These techniques of tomography and efficient tomography has been successfully tested in our case study using real seismic data. Now I would like to pass the button to Mr. Abdelli to continue the remaining parts.
Good morning, everybody. My name is Malek Abdelli. I'm a geophysicist. I'm a director of processing center. As you can see, our case study is from the processing. So we are not acquiring data. We are just using the data that was acquired from 1997 to 2017. Our area of a project is, this is the most difficult. It's 15,000 square kilometers. So how we are going to unlock the subsurface image or the near surface image? Because in the oil and gas, we still have big necessity to understand what is the near surface. It's acting on the ray path that we are using for the imaging for the oil and gas. So here, for example, this is the area that we are using, all the 15,000 square kilometers. You can see the line, the black lines, and how the elevations are so variable. So we have like from 150 meters until 70 meters difference. Okay. Here, for example, there is another program conducted exactly similarly with the seismic acquisition, which is the Apple program. So for each program of these 15 programs, we have a different. So how we are going to use this data to unlock the uncertainty of the near surface. Okay. Building of the L-level model, which is the low velocity model. The near surface, okay, or near surface, for us, it's the low velocity. For the heating of the first bit of the refractor wave, offset to 10 meters to 1,400 meters have been retained. This is just to build the first model, okay, that we are going to use in the tomography. And you can see there is a very big variation even in the heating. So our results from the first time is low quality to get a good subsurface and water. Okay. Unfortunately, the 15 programs, seismic programs, give a good reflections. So sometimes we have a good peaking, sometimes no, due to the noise acquisition. By using this tomography model and using the first initial model from the Pfaffhuber or linearized model, we can see the results that we get. Okay, tomography was chosen since it's looking all the lateral variations of the propagation velocity. So this iterative process involved comparing observed first arrival time with the predicted arrival time based on initial velocity model, updating the model parameter for each iteration until satisfactory match is achieved between observed and predicted data, which is the tomography tomography. Here, for example, I will present some QC because the main thing is does the tomography is doing a good job over the whole project and over all the 15 square kilometers. Here, for example, we use a different offset range, and this range is not separated. So we start from 0 to 400 meters, then we add more offsets. So to see if our tomography is going to do an inversions and have a good quality on the site. Computation of static corrections. This is the second mode because when we are using the tomography, is we are calculating or inversing first directly by minimizing the error between observed time and the measured time. But the real thing is how to calculate the primary static that we are going to use on the process, on the same process. So here, for example, we are using the computation of static corrections was done using the pseudo-datum plane to calibrate calculation static model. We used the elevation of the first layer of the upper model as a pseudo-datum. This aimed to all the static models, inversion, linear and non-linear, have the same level of the static. So we are using the pseudo-datum, then we are going to the final datum after in the stack steps. Okay. Static corrections, depth penetrations ranging between 1 meters and 150 meters. We can see this is the penetrations method. So we are using the first peak that we measure it, that we pick it, okay, inverted for model velocities, and we see the results. We have a good matching between the depth penetrations and the elevations. In below we have the homostatic solutions. We can see, for example, here the results of the three methods. So we have a good matching, of course, between the statics or between the depth penetration of each method, uphill or generally the line or diagram or a tom. But the tom one, which is it gives the better model approaching the altimetric match. Another QC, for example, you can see here some shots in seismic. So we have an offset going until 5,000 of offsets. Okay, applying the static, align the refractions. So from this, we can see if we have a good static or no, before doing some advanced processing or stacks or migration to whatever. Applying static value is necessary to check the results on raw data as an example. The analysis of the reflections with and without applying statics help us to evaluate the quality statics. Now I'm going to show you some examples of seismic sections. Okay, this is 3 or 4 projects. So we did some harmonizations of the data seismic, then we apply the static. So we can see the static done with the tomography method vs another methods. And we can see that we are going to take some quality, some resolutions, comes with the same data as the circle, the red circle or the arrow. The same here, for example, it is another project from the 15 project. We can see the low frequency, for example, data, and it's going to be processed right now. Because this project is ongoing. Right now it's in migration, in PhD, by migrations. Okay. Tomography or the other side methods. I will show you some sections. So you can see here the red, it's different projects. So we have different faults. The black line is the elevations. That's it. So this one is the altimetric elevations, correction static from elevations. So I will be flip-flopping between methods, so you can see the difference and the importance needs to get a good statics. I go to the other one, between DLM and GLI. So you see some fluctuations. We don't have a very big shift since we are using the same pseudo-datum. And finally, we can see the tomography and how all the data was aligned, and we get our resolutions as an initial for this set of data, because we still have to do more processing work. Here's some interpretations, so we give to the interpretations to see if our statics are correct. So we have confronting our data with the model. We have many wells, so all the interpretation was there. The final QC is made using seismic calibration between the wells that are of the seismic. I will go directly to the conclusions. The use of this process has generated accurate image of subsurface structure. I'm talking in a deeper part. So knowing the near geophysics, we allow to us to have a good image in seismic. And even in the BSDM, for example, in the depth migrations, it's more important to have the velocities of the first near surface. Okay? In proportion to detect the steeply deepening feature to provide high resolution image of subsurface. Thank you.
And Mr. Shri. Now, as I can see, a lot of you are feeling sleepy. Don't worry, we are just left with one more technical talk for this session. And please invite Mr. Kripal Chaudhary from AMBER. He is a geophysicist and business manager TSP. Please give him a huge round of applause.
Okay, good afternoon to all. Myself Kripal from AMBER, India. I'm a geophysicist. So I will deliver a presentation on integration of wireless seismic reflections using mechanized source in hydro tunneling. So when we talk about tunneling in high mountain area, we always say that when we are building a tunnel in high mountains, there is a vital necessity of investigation during the construction phase. And we all know that many construction industry are using many types of methods like face mapping, road mapping. They do probe drilling also. And there is one more method like drill parameter analysis, we can say MWD, measuring by drilling, and the geophysical method. So when we talk about all these surface methods like face mapping, road mapping, we all do some observation from the face. On the basis of the observation, we say like yes, the ground can be some poor or it can be good ground. And another is like a probe drilling. The probe drilling also giving a very good information, but it is also limited in terms of information, like you can say it's a short information, short range information, and another is like it's a point information. And when we talk about MWB, it's also another type of probe drilling, which is also like expensive and time consuming also. So another technology which is also common nowadays in India, where during the construction the people are also using geophysics during the construction stage for the investigation. And one of the methods which is now very very common now in tunnel industry, that is the TSP. We can say the tunnel seismic reflection system. So what this system can do? You see, the system is a geophysical method. It's based on the principle of seismic reflection. So like we know that from the surface seismic investigation, we always have source and receiver on the surface. But now, in case of this tunnel seismic, we have to plan our shore and receiver points underground. Like the shore is also inside the tunnel, and the receiver is also inside the tunnel. So depending upon this reflection survey, we can measure the velocity in terms of P and S waves. And on the basis of the velocity, we can derive some geotechnical parameters, and we can have the information up to 100 to 150 meters ahead of the tunnel face, depending upon the type of source. And the results also can be evaluation can also be done very fast in 5 to 6 hours with a high accuracy of around 85 to 90%. So that was the information about the system, which is based on the principle of seismic reflection. Now, whenever we talk about any type of technology, we also have to see the history of that method and how many years people are using it and what are the information, whether it's giving good information or not. So the system is, the technology is quite old, started in the 90s, And now, recently we also introduced a next generation system, that is TSP 603 impact system, which is basically the same technology, but it's a wireless seismic where we are using a mechanized seismic source like a TSP impact hammer. So now, when we talk about explosive and mechanized source, both are different sources, but with the help of both sources, we can have good information depending upon the frequency component. Now, if you see on the left-hand side, this is the TSP layout when we are working in the drilling class environment by using explosive as a source, and the right-hand side is also using the TSP method with mechanized source like an impact hammer. So when we are working in explosive, we always have to consider short points and the shear points according to a particular tunnel phase. But when we are working in a TPM environment, we always have different short points with reference to a new phase position. So on the basis of the everyday mining, every hour mining, we have to have some new short points. We can say it's a construction stage according to the mining progress. So next slide shows you the frequency components also, because we also need to know that what are the frequency components we can get from seismic method. We know that with explosive we always have high frequency components. The left hand side shows you the frequency component when we are using explosive. So we are able to get up to 100 to 1150 Hz. So because the system we are using high frequency information. And the right hand side shows the frequency and spectrum in case of the hammer data. So you can see for both of the spectrum was acquired from a single type of rock mass. The rock mass was the competence schist. So the comparison can be seen from this slide that in case of the hammer also, we are having some low energy, but we are also getting good frequency also, like up to 100, 800 Hz we can receive. So we can say that the spatial resolution also, the hammer is also giving a good spatial resolution, but it is slightly less than when we are using explosive. Now I will show you a small video like how it works in a tunnel. Because the environment in a tunneling is always different, we don't have access to the phase, we don't have access to the rock mass. We have to work according to the ground. So this is the mechanized impact hammer. So we have to install the system in the TVM, and the system is complete wireless. So by using some wireless signal, we can command to the system that whenever it is required, it can go and hit on the tunnel side wall. So, and when it is hitting on the side wall, so that the receiver which was installed behind this tunnel face, they always do recording whenever it is needed. Now I will show you a case study. We know the system is good, but I always try to do some comparison. Whenever we do some TSP, we always have to compare whether we are getting good information or what is the accuracy level. So for this case study, I try to compare the TSP data with the actual ground condition which was encountered and the anticipated geology also, like what was the anticipated geology according to the geological baseline report. So that was the case study. So for this case study, I use 3 TSP campaign. If you see here on the right hand side, there was expected fault or shear zone, which was expected according to the geological baseline report. So and this red arrow shows the location of the 3 TSP campaigns within that area. So I try to study this, and according to the information available there, so within that zone, the geologist was expecting that within this fault zone, they will have a poor rock mass with an RMR value of less than 20 meters. So that was expected, and on the basis of this expectation also, the TSP was carried out. So now I will show you the output of all these 3 TSP campaigns within this study area. So the first rock property charts means like you have information about the velocity and the parameter estimated from the velocity. So the first row property chart is shown here, like it shows the variation of the velocity on the upper part of the image, the P velocity, and the bottom is the S velocity, and then another two parameters which are the interaction relation formula, like the Poisson ratio and the dynamic modulus, which can be estimated on the basis of the velocity. These are the dynamic parameters. So this is the first output from the first TSP test, and on the basis of the fluctuation and the fluctuation in the value of the velocity, we try to find out the information that, okay, yes, this drop in the velocity we can tell it, okay, it's a zone 1 and this is second is a zone 2. And the same thing we also can see in the velocity distribution also, like you see, there is a tunnel phase, and ahead of the tunnel phase, according to these two, zone 1 and 2, we can also see the drop in the velocity, where the velocity was dropped as compared to the surrounding and the reference value. And this is the second zone, TSP number 8, which was the next location. And but in the second TSP 8, we always have some correlation, like overlapping also. Like if you are having 100-meter prediction, so for the next TSP campaign was done before 20 or 30 meters. So the next and the remaining 20-30 meters are like a overlapping area. So like if you have some zone 2, maybe it is in the end of the prediction, we can see the resolution can be down. So the next TSP campaign, we will have the higher resolution to compare this in the down also. So this is the second one. And this is the velocity information, like 3D velocity information. So you can see the zone also in velocity area also. And this is the third number, TSP number 9. Yeah. So it's also giving some information about the velocity, and then we categorize them in zone number 3 and 4. And now, a part of these velocity informations, like we know that, okay, in some area we are having some low velocity zones. This low velocity zone, we need to know, okay, we need to, how is the distribution of these low velocity zones in the tunnels, whether they are dominating on the crown area, or whether they are cutting the tunnel axis, or whether they are going or they are crossing which angle. So that type of information is also possible. Like if we know that there is a low velocity zone of around 3,500 meters per second, so we can see where this velocity is going on in the space. Like you see the surface rendering features also. Like I mentioned the zone number 1 and 2 in the first slide of TSP 7. So you can see the surface rendering feature also, like the first low velocity zone, second low velocity zone. And if you go for the second zone, second TSP number 8, you also can see the rendering features depending on the velocity which we receive there, and this is the third one. So all these three, like you can see in the 3 dimensions also how the feature are in the tunnel. And now in order to compare this information, like that was the information which we received from the seismic data. But in order to compare this with the reality, we try to compare this information with the TPM parameters, because in the TPM we don't have access to the phase, we don't have phase loads. So we only have some mach information, we have some TPM parameters. So here I try to compare the dynamic young modulus, so dynamic young modulus which I try to estimate from the velocity. So I try to compare the dynamic modulus with the TPM contact force. So because the TPM contact force are proportional to the rock strength also when it is increasing. So if you see 3 zones here, the zone number 1 where the TPM parameters are getting down, the values of dynamic is also down. And if you see the second zone, which was expected a shear zone within this fold zone, and this is the third and fourth zone. So all cases with some up and downs, we can say it's a very good correlation with the dynamic value and the TPM contact force. And this is another observation that we received from the mach information also. Like within the same area, they try to have some mach sample also. So this was the information of the geology found in this low velocity area. And now come to conclusion. we can say that for this present case study, critical areas such as shear fault zone, which was given in the GBR report, but exactly it was not a fault zone, but the client found that there was a disturbed zone, not like a fault zone, but there was some shear zone was available and which was given by our TSP also. So the prediction of around 80 to 100 meter was achieved in this case. And even though much less energy introduced in the ground, the impact hammer, when compared with explosive, the sufficient spatial resolution is achieved for identifying these geological surprises. And the total 28 number of campaigns so far have completed within this area. And where I only showed you three only. The tedium parameter, in particular the contact force, is a good agreement with the forecasted witness zone. The new mechanized source can be clubbed with a tedium cycle where to explore the promontory Thagabias zone. And data acquisition doesn't have any impact on the tedium production cycle because it doesn't need to be slow. So the acquisition can be done during the mining always. So that's all for my side. Thank you very much.
Whom you are?
Yes, sir.
Is it a controlled source?
It's a control source. It's a control source.
The signature you define it that accordingly as happens in right
Yes, you see, we are using this impact hammer with a specific, works on a specific pressure. So we can say it's a 7 bar, you can set it to 7 bar and then every time 7 bar pressure is it. So that is the control source.
And I mean, in what way, is it a horizontal kind of a direction in which you...
Yeah, you can say it's perpendicular to the wall.
Perpendicular to the
with a slight 1 or 2 degree downward. Because the tunnel is circular, so we try to make it a little bit downward so that complete.
Has it something to do with the kind of wave which would be generated, which would be significant?
Yeah, you see, like whenever you have some more like a little downward, it always helps the generation of the S waves also for that purpose.
Thank you.
Thank you. So, yeah. Professor Sastry.
For the same speaker, I just wanted to have some details. The 3D disposition of the weak zones which you have depicted. So normally for that you need more number of receivers. But how did you manage with single receiver?
No, we have 4 receivers, sir. We use 4 receiver and 20 to 24 short points. And the receiver is a multi-component receiver, like we are having 1 component of P and 2 component of S. So on the basis of this, we are having information.
Yes, this is a question to the first speaker. So we just want to know what is the exact technology which you use for aerial survey, and what is the depth of penetration which you could achieve?
So the Indian survey in the Himalayas, it was a Skytem helicopter system, a 306. So that is their stronger system. You have different systems that are either tuned for the highest resolution or the deepest penetration. What we used was not the strongest, it was one of the stronger ones. And we achieved a depth 600-ish meters, a little bit less, a little bit more, depending on the actual geology around that.
Yeah, I'm Gopal Dhawan. My question is to Andy, the first speaker. You presented a very interesting case study for conducting EM surveys for Himalayan tunnels. And I think you were doing it for I think for the last couple of years, as I heard that so many tunnels have been investigated with this technique. Is there any case study where some comparison has been done between the predicted and the actual geology based on AEM or magnetic survey?
From the work we've been doing in India, it is that first example that I showed, that is we only have the oral confirmation in the field that this was aligning with what they experienced, when we didn't get any, any records like the TBM records that were showed. We didn't have that. We have another case study back from earlier days in Norway, where actually the geophysical model and also a ground-based EOT model were compared in detail with the face mapping, with the geological mapping on the face in a very complex sedimentary rock environment, heavily folded shales, black shales, limestone-based shales. So that is something that I can happily send you.
Okay, thank you very much. I look forward to it.
Yeah, actually I also have one question about around 600 meter depth penetration. So what was the real target, what was the expected depth you were looking for that? You achieved 600 meters, that's okay. But what was the level of the tunnel, or whether it was within that 600 meters or beyond that? And what is the maximum depth you can achieve? And another thing is that here it is a very tedious work. So how much time do you need for the preparation? Suppose we want to go for this work or any tunnel. So before that, what are the main clearances and how much time do you take for all these clearances if you want to go for a new area?
Yeah. I'll try to answer the first question first about the depth penetration and what was really demanded and what we were hoping for. And that's not an easy answer to give. It's a complex setting. Of course, we were really trying to be able to penetrate this as deep as possible. But that is still bearing in mind that the strongest system that you could use wasn't really applicable for the extreme setting, because that is even heavier and even more difficult to fly in these extreme altitudes. So we had to make some trade-offs there. The overburden towards the tunnel was up to 2 kilometers, right? So way more than 600 meters or even 800 meters if you achieve it. So there is always a trade-off that obviously towards the portals, when the overburden is limited, you get a really good coverage. But when you get to the areas where you have kilometers of overburden, of course you don't see down to the tunnel any longer. But we have had experiences in the Andes in a similar setting where, well, even though we couldn't penetrate all the way down to the tunnel, we could see really significant features where there was a suspicion for weakness zones, but they weren't confirmed. They were just, based on topography, you can see, okay, there's a gap, there might be something. And in our models, we can see, okay, this one, there really seems to be weak material, and we could also see in which direction it goes down. So then you can make an extrapolation and say, okay, it might hit the tunnel at this kind of, but there is more uncertainty, of course, involved in that. And what is the deepest that is technically possible? Just a month ago, some of the latest results from one of the French volcanic islands that I don't remember which one, Réunion or one of those, where the French Geological Survey was using actually 3 different SkyTime systems, from the highest resolution one to the most powerful one, and flew them all at the same time to really, because they also wanted to look as deep as possible, and there was even more than 1 kilometer. So but I've never ever seen that before. Otherwise, that is normally when an airborne geophysicist tells you I can look 1 kilometer, then you, yeah.
About 1 kilometer. About 1 kilometer.
1 kilometer.
1 kilometer.
Yeah, is stretching it really. I would say in most geological settings it's impossible, but in that particular setting, it was volcanic, very high activities. It seemed reasonable. That was the first one. The second one was about timing. This is you will never have it within weeks. That's impossible. but in a best case scenario it can take 2 months. In a worst case scenario it can maybe take half a year, but that is, well, we've actually no idea. But it very much depends on, of course, where and in which stage.
Depends where it is being surveyed and what.
Yes.
So we'll take last question, and then during lunchtime we can have further discussion.
Thank you, speakers. Okay, we are all professionals here, but the question is from a layman. Let us suppose it's from a layman. Untouched mountain areas, fragile ecology, Himalayan areas. So, what would be a better option? Not to have developmental activities, so much developmental activities like tunneling, road making, big dam making, or some kind of...
Can I interfere here, sir? I think that we can discuss. If there is any other specific question to their presentation, that we can take up. That is policy decision and things like that. So, any specific? Yes, last one, please.
So my question to Akhil Mishra. Akhil Mishra. Yeah, when you have collected the airborne magnetic data, you are applied extended Euler depth solution for estimating the depth. How did you calculate the estimated depth from extended Euler depth solution? Generally, it is Venner solution for one-dimensional data set.
And there are many methods for magnetic data interpretation, like quantum deconvolution, Alert deconvolution, and then NLT signal, many methods. But the problem is the how constant solutions, because they all give spray of solutions. So, like in this method, one equation is Euler equation, otherwise simultaneously solving Euler equation as well as extended Euler equation. So we get two depths. Now from two depths, now we take difference between these two depths. Where the difference is less than 10% or 20%, depending upon our objective, we can take, otherwise other depths can be rejected. This is very well established and published in Musa 2001 paper. They have given this is Euler solution, this is external Euler solutions, and how they are merging together across.
You have applied any spectral analysis?
For this case?
Perfect. Yeah.
No, I am not spectral analysis.
I would like to thank all of you for the patience hearing and.
I would now like to invite our chairperson for the session, Shri Kapil and Dr. Tiwari for the memento presentation. And I request all the authors to please stay back for a while. First one is Dr. Andy. Please keep giving that. Thank you. Next one up is Dr. Akhil Mishra. Round of applause, audience, please.
Thank you.
Next one is Ms. Keditja and Mr. Malik. And the final call is for Mr. Chaudhary. Thank you so much. I would request. In this very hall itself, and we'll resume back for technical session 2 at 2 o'clock. Thank you so much.
And lunch is being served in the exhibition area.
Lunch again is being served in the exhibition area itself.